Hey everyone, as promised, I told you that I would finish up the example problem that we started in class today. We did parts A and B in class, and I told you that I would record the answer to C and post it for you so you could take a look at it. So I'm going to do that now. But just to reiterate, so we remember where we were, I'm going to run through A and B again. I won't do the whole problem again, but just kind of try to refresh your memory of what we did. So part A says two boys are pulling on a box as shown below. It says if F1 is 50 degrees, F1 is 50 newtons at 30 degrees above the x-axis, F2 is 100 newtons at 60 degrees above the x-axis, find the net force acting on the box. We went through, we talked about the idea that the red one represents F1, the blue one representing F2. I moved them, but originally we had them set up so that they were tip to tail. And then we drew in the purple vector that represented the resultant vector. Because we said that's really, let me get rid of this. Ooh, not clone. We said the purple vector really represented the resultant vector of the red and the blue, which is what the net force is. It's the resultant force. So taking these red and blue ones, because neither of them was on the x or y axis, we brought them over here, and we broke them up into their separate components, found the separate components there, and we said that each of them has an x component, each of them has a y component. So we took the x and the y component, or we took the x components of both of them individually. Because they point in the same direction, we can add them together to get a total of 93.3. Then we took the y components individually, and once again, because they both point in the same direction, we can add them together. We got a total of 111.16, and we said that gave us one big right triangle, where we knew two of the sides, so we could calculate the third side, and then we could figure out the angle as well, and that gave us a resultant force of 145.5 newtons at 50 degrees, or 50.1 degrees above the x-axis. And that's the answer to question number 1, which is the net force acting on the box. Then, for letter B, it said if the box had a mass of 125 kilograms, what was the acceleration of the box neglecting friction? So in this case, we're just using Newton's second law, right? So in Newton's second law, we know that the net force was 145.5, so we just plug that in there for the net force, 145.5 here. The mass of the box was given to us as 125 kilograms. We solve for the acceleration. We get 1.16 meters per second squared. Once again, the direction, because it's acceleration, and acceleration is a vector quantity, it has to have direction. That acceleration is going to be in the same direction as the net force that we calculated. All right, let's go on to part C now. I'm going to grab this and start myself up a new page. For part C. Part C says, if the actual acceleration of the box is 1.0 meters per second squared, what is the coefficient of friction between the box and the floor? If we go back to our picture showing us the net force, in problem A and problem B, we neglected friction, so there was no friction. But in part C, there is some frictional force now. We know that friction is an opposing force. It acts opposite of motion. In part B, we established that the motion was in exactly the same direction, or the acceleration, which is the motion in this case. The acceleration is in exactly the same direction that the net force was being applied. If that's the case, and we go back to this picture, if the motion is occurring in the direction of, if the motion is occurring, hold on, if the motion is occurring in the direction of this purple arrow, that means that the frictional force has to be exactly opposite of that motion, or opposing that motion. Remember, friction opposes motion or an applied force. In this case, it's opposing the motion and the resultant of those two applied forces. So friction represented by the green arrow in this picture. Using things that we already know, right, we can go and start working on this problem. Here's Newton's second law. We already established in part B that the net force, or the resultant force, of those two applied forces was 145.5. So we'll call that F resultant, because that's what I thought of on the fly. But now there's another force that we have to add into this equation, and that's the kinetic friction force. This doesn't change the way that we do the problem. It still ends up looking like a Newton's second law problem, even though now we're in two dimensions. If we're going to find the coefficient of friction between the box and the floor, remember from our formula, there's our formula for the coefficient of friction. If we want to find the coefficient of friction, we need to find the force of friction and the normal force. If we take a look at how we manipulated Newton's second law here, right, kinetic friction is part of that equation. We've already established the fact that that resultant force between the two applied forces was 145.5. We don't know what the frictional force is. It was green, right, on the drawing. But we do know what the mass is. It's 125 kilograms. It told us that in the last problem, or in part B. And also, in part B, we calculated that in part C, it told us that the actual acceleration was 1.0 meters per second. It slowed down, which makes sense, because friction is the opposing force, blah, blah, blah. You run these numbers through, and you should end up with friction being equal to negative 20.5 newtons. That gives us 1 part of that coefficient of friction formula that we need. The second part, the normal force, we're going to make use of something that we talked about earlier in class today. If we look at this free body diagram that we've drawn for our object, we're looking at it from an overhead perspective. And that means that the gravitational force doesn't show up on our free body diagram. But that doesn't mean that it's not there. The gravitational force is still acting on that object, and that gravitational force is still equal to m times g. It always is, even if it doesn't show up on our free body diagram. It just so happens, like we talked about in class this morning, that gravitational force is acting into the board or into your screen. If it's acting into the screen, that means that normal force has to be acting out of the screen. Those are the only two forces that are on that additional axis, which we could call the z-axis if we wanted to. We usually call the horizontal axis x, the vertical axis y. We usually call that third one the z-axis. But on the z-axis in this problem, there are only two forces. Gravity into the screen, normal force out of the screen. And that means that normal force has a magnitude equal to the gravitational force. Because there's only two forces there, it's not rising up out of the page or falling into the page. At least we're not assuming it's not going to. So that means that the normal force has got to be equal to m times g. That takes us back here. Now we have a way Now we have a way to figure out the normal force in this coefficient of friction formula. So if we take it here, right, that means that the coefficient of friction is going to be equal to 20.5. Remember, in coefficient of friction, the direction doesn't matter, so we don't have to worry about that. Divided by 125 times 9.81, which I will punch through here pretty quick. And that gives me 1,226.25. Calculate that out. And I end up with a coefficient of friction equal to 0.0167. That's pretty involved. Lots of steps, but not out of the realm of possibility for a test question. So there's part C out of example problem number 4 from your problem set. Questions tomorrow in class. Remember, test on Monday. We'll handle questions about it in class on Thursday. Talk to you later.